Good afternoon, everyone, and welcome to the third webinar of the 2022-2023 IMOS webinars program. My name is Caterina Giusti. I'm Professor of Statistics at the University of Pisa in Italy. As a member of the IMOS team of my university, I am working at the organization of the webinar program on behalf of Eurostat, together with the German company Startup. Today, I will act as the webinar moderator. Now, let me first explain for any newcomers that IMOS stands for the European Master in Official Statistics, a joint project of universities and data producers in the EU member states, EFTA, and EU candidate countries. If your university is interested in applying for the IMOS label, please consider that the permanently open call for universities is available on the IMOS dedicated page on the Eurostat website. For staying in contact with the IMOS news and community, please follow the IMOS Twitter. The Twitter handle is @EU_IMOS. It's now time to start with our webinar. Before I give the floor to our speaker, let me first briefly explain how we run the webinar today. As you can see this here, the IMOS webinar stream on Zoom. The webinars is recorded. The recording will be uploaded on the IMOS YouTube channel, where you can already find the recording of the past webinars, as well as the past 2 IMOS workshops. As a participant, you can watch and listen to the webinar. You can also use the Q&A manager to pose your question to the presenter during the webinar. Should you have any technical problem or question, please send a message in the chat and you will be contacted by one of the members of the technical staff. So today, we have the pleasure to host Professor Ralf Münnich. Ralf is university professor, chairholder of the Economic and Social Statistics Department at the University in Trier. His publication focus on survey sampling methods, data quality, computational statistics, indicator methodology, and the modeling of imprecise data. He was scientific coordinator and responsible, among the others, for several European projects. His latest research focuses on advanced sampling methods for integrated surveys, use of new data, and microsimulation methods. He is running a research unit of the German Research Foundation on Statistical Microsimulations. Ralf is currently president of the Research Institute for Official and Survey Statistics, and since 2020 is chairman of the German Statistical Society. So today, Ralf will present about non-probability sampling and big data. So Ralf, the floor now is yours.
Thank you very much, Caterina, and thank you also very much for the invitation to this IMOS lecture. A long time ago, I did that before, and now it's a really great pleasure to come back. Today's topic is not on microsimulation methods, but on non-probability sampling and big data. Some of you have been in the research infrastructure INGRID, like Caterina, and we did some research there, and I want to show a little bit the problems. So more the contrast on classical sampling versus non-probability sampling, and partially also with respect to big data. Let me start with an example, and the technique fails immediately now. The problem is, of course, widely spread and well known since nearly 100 years. And I refer to one very old example that was the Gallup opinion poll in '48 about the US elections. And at that time, Dewey from the Republicans versus Truman from the Democrats was to be elected. And Gallup used the quota sampling, and the prediction was Dewey. But, well, the problematic thing is it stopped also a little bit earlier, not directly at the day of the elections. And finally, the winner was Truman. And of course, this was a little bit a delicate problem, since everybody was discussing what happened at that time. And I think many people said that we have to consider more a real random sample rather than these kind of quota samples. Well, certainly we know that quota sampling can be a random sampling, but it's a little bit sophisticated. Similar examples came later, like we know Boris Johnson's red bus for the Brexit, and that also influenced a little bit the voting examples, or the Trump elections. And we will come to the Trump elections a little bit later in terms of big data and see what happened then. In Germany, since a couple of years, we have really a huge debate on that. And it's basically market and opinion research versus internet surveys. And what's the big question here? Well, market and opinion research claims that they go for classical probability samples, and they claim that these internet surveys are somehow samples which are not collected in a random way and hence are biased. And so the basic question is non-response versus web selectivity, because the internet survey companies claim that in market opinion research, we have more and more to do with non-response. And the question, what is better? And that's really not easy to answer. For sure, as you will see, we are in favor of classical survey-based or sample-based surveys. But the problem of non-response, once you have, let's say, 80–90% non-response, of course, is really problematic. And certainly in this context, we always ask ourselves, what is a real good survey? So that was a little bit kind of prelude of the presentation. And I first start a little bit with statistical inference and quality. So what is behind that? What do we need? What is the classical focus? And why do we go for other things? Then we talk a little bit about compensation methods. Here I will focus on weighting methods. That's the classical thing. Certainly I know a lot of model-based stuff in the meanwhile is done. Katharina is well known in that area with small area statistics and use of big data. Then I will turn a little bit to examples, web surveys, and especially the wage indicator survey, which we had in our big project, the research infrastructure. And I will tackle also shortly 2 examples from big data. And finally, I try to conclude, but don't ask me for recommendations. It's not really so straightforward and trivial to answer. Whenever we talk about classical statistics, we focus direct on a general idea of estimation. So we have a population, we draw a sample, then we have our sample here. And from the sample, we get our estimates. The question, of course, is, what is the sampling process? So this direction is very important. Is that really a classical random sample, or is it more focusing on selectivity? That's a big question. And certainly once we have the sample and the parameter of interest estimated, the question is, well, do we really cover that, or is there kind of gray area? And can we somehow focus how far is the estimated parameter away from the real parameter? The question is, of course, can we really estimate that, or can we, in what focus can we do that? And of course, that is what we call inference, or in this context, one step could be, of course, interval estimation. However, we could also phrase it in terms of hypothesis testing. So like we have the analysis of a sample, that's the estimation process. If we have information on the random sample, then we can somehow use normality in some cases. We have the sampling distribution around our estimate here. It's a classical mean, made it somehow easy. Certainly we can think probably we have a hypothesis that our mean is somewhere else, especially in poverty measurement. Sometimes we have the classical focus saying, okay, at least 20% are in danger of poverty or something like that. The problem, of course, is we don't know the truth. And the truth could be anywhere. It could be close to the hypothesis, or it could be completely somewhere else. But here you see we somehow have this kind of spread of the normal distribution. And the problem, of course, is how do we get that information? And that, of course, has to do with our classical context of inference. And the question is, what of this can we maintain if we go to non-probability samples? And that's, of course, much more sophisticated. And within this context, we also ask ourselves, even if we cannot do the classical inference with these kind of figures, what does quality mean in the context? And well, I certainly refer, what else, in the Amos lecture to the European Statistics Code of Practice. For sure, I don't tackle all areas, so only some of that, and which might be of interest in terms of this lecture. Well, relevance of statistical concepts, that's of course in all cases. We need to know what the user wants to know, and then we can set out a survey. So that focuses certainly on the sampling based, so the probabilistic surveys, as well as probably the other techniques and non-probability samples. Certainly, there might be some hierarchical structure. I phrased already small area estimation. That's another sophisticated story, because then we have this kind of combination of classical inference plus model accuracy. And once I talk about accuracy, that's really the statistical challenge. We know that by detail the sampling errors, whenever we have this kind of sampling inference, we can somehow calculate standard errors. Probably we're interested in confidence interval coverage. That's dangerous, because whenever we have one sample, we cannot talk about coverage probabilities. That's only possible in simulation experiments. But of course, kind of confidence gives you some information on quality. Unfortunately, we have these problematic parts like non-sampling errors, one of which is non-response. I phrased that. And more nowadays, we have the difficulty that many of the surveys are somehow affected by high non-response rates. Well, official statistics, especially if they can go for mandatory surveys, don't have these severe problems, but for voluntary surveys, like in Germany, we have, in the meanwhile, non-response rates which are upon 80%. And then, of course, the question is, how much is the inference somehow influenced by that? Well, coverage problems might occur, certainly. Well, and that's obvious. Like, if we go for web surveys, do we really get the right coverage of the people? Are some dropped by these kind of things? And measurement error is something different, of course, but this also has to be considered. The other thing is, of course, timeliness and punctuality. Well, if you go classical survey samples in the probabilistic manner, often it takes very long to gather the information. So the duration from acquisition until publication may be very long. And that seems to be kind of a very clever thing for web-based surveys, because here we get in some streams, we kind of time by time can calculate new values. But of course, the question is the coverage. It's kind of contradiction. So we see already that these aspects have to be considered in different ways. Coherence, comparability, accessibility, and clarity, of course, that's something which has to be considered by all of them, and completeness. And there's for sure some more of these things. Nevertheless, we have to talk about some details on what we really have to consider in the future. And I put it more in this kind of modern text like data science. So all requirements of the previous slides have to be met in general framework of data collection in what we do. And of course, we ask ourselves, is the frame or core population known, well addressed? How is the data gathering process controlled? And that's the real big issue. Like, if we set up a survey in the internet, who knows from this internet page? And how can we control that? That's really a very difficult thing. Is every unit separately drawable in a completely known way? Does every unit provide full information? Non-response is also here probably a problem, but not in the context of unit non-response, more in item non-response, or that people look at the survey and drop down, and you have probably not really the big information on that. Are there any other sources of imprecision? Is the measuring process adequate? Note, possible sources of imprecision have to be controlled and, if possible, measured. The output has to be evaluated in light of the data gathering process, including all these drawbacks. This includes also possible corrections of the results. So what kind of corrections are meant, and what is the real challenge of non-probability samples? Well, the big difference, of course, is that once we go to non-probability samples, we have kind of uncontrolled, probably non-random generation process. Well, the danger with non-random is, of course, most of the techniques we use later on is we assume kind of model, and all these models have kind of random term inside. So it's a dangerous process. So I prefer in the meanwhile say uncontrolled or not known gathering data generating process. Certainly we have missing sampling information. In a controlled survey, you generate, well, from a frame, you draw samples, and then you have some information on how you sample. These so-called inclusion probabilities, pi I in our context, probably also the second order inclusion probabilities. if you are interested in variance estimation, quality measurement, you truly need that. That has to be known, and that is a big lack in these kind of surveys. So then also the coverage of the target population is not assured. With sample surveys, we always try to take the coverage entirely. With these kind of non-probability samples, it's not that easy to control the entire target population. So these kind of inclusion probabilities which vanish is possible, and that means automatically biased results by definition, as we can prove that. You may be on the lucky side that it's ignorable, but that's not clear in advance. Possibly we have a poor representativity, selection bias. There are many examples. I heard from several surveys, like from Switzerland and from the Netherlands told me that they went for surveys and there was a certain small group, religious group, interested in the outcome. And even small groups, if they are really very active on these kind of surveys and the sample sizes are not big, they can heavily influence the results. And you must be sure that these kind of self-selectivity cannot spoil the entire results. But usually they're of much lower costs and probably also faster. Remember the example of the election. I will come back to that later. In general, if you do a good web survey, you have really very fast results. And that's the big thing. And that's why politics, at least in Germany, is so much interested in it, because overnight you can get some information. Nevertheless, the question is how good and how accurate is this quality? And often it's easier to obtain certain variables. But is it cheating if you ask kind of critical questions? Some people want to answer, others don't want to answer, are dropped down, but then you think you have a lot of answers in this respect. To put it in a more general framework, we try to write it down in this way. So we have the non-probability samples. Then we have response reference data. In general, this is a sample-based survey. And the question is, where are the advantages and disadvantages in terms of availability of data? And certainly with the response data, we have survey weights, probably we have calibration weights or whatever additional weights, but maybe, and that's the critical issue, this kind of target variable is lacking. Then you cannot estimate that. I will not here tackle the problem if auxiliary information is missing and we substitute that by big data. I think you can ask Katharina about these kind of questions. She knows a lot in that area, but here I'm focusing on this case. In non-probability samples, of course, we have the opposite. We are lacking in design information, but have an awful lot of variables available, and especially the target variables. Additionally, we added here kind of calibration target data. So probably we have additional target data where we have some additional calibration weights. Well, these can be just one data set, then of course this would be fulfilled. But the important thing is that we tackle it here as the target variables are somehow lacking. And our question is, how can we somehow treat that? So the one thing could be like, we want to take the non-probability sample because here everything is available except the design weights. So we use kind of response variables, like from the response reference data, we model that or weight that in a way that using the response variables, we somehow construct design variables and eventually also calibration weights. We will see that as long as we do just weighting procedures that somehow seems to be straightforward. I think the most well-known is propensity score weighting, which is widely used in social sciences. Next thing, of course, is that we directly go for calibration, and so we use the calibration weights. So try to ignore the design weights. That's a separate kind of process going directly to the final weights. That is implicitly also done in weighting. Sometimes you can somehow combine that. Nevertheless, there could also be another attempt saying, okay, we try to construct the target variables. So here we will use the probability samples, either in the first case or in the second case, but we use available information from the non-probability samples to somehow either impute or whatever, or predict the target variables. That's the alternative way. And of course, the question for us is, what is better? At least if we do this, then it seems that we can use the entire inference of the sample surveys, which seems somehow convenient, but often they're very small. And the question is whether it works. And I can already say, here we might have the problem of the availability, or what kind of model assumptions do we use. I shortly tackled a little bit the kind of weighting procedures we might be interested in. The classical is, of course, modeling the response process. So the approximation of unknown inclusion probability, so the participation probability. And that's basically nothing else than the probability to respond. Certainly, we can also balance that on some additional auxiliary information, but that's the classical way we want to treat that. So it's the set of observations outside the non-probability sample required to estimate this kind of model. The straightforward way is the response model by logistic regression on response variables Z using the parameters omega. So it's a classical model. So we try to estimate the somehow inclusion probabilities to attend somehow our non-response non-probability sample. There are some technicalities. Of course, it's straightforward. We take the binomial log likelihood or pseudo log likelihood, whatever you want to take. There are some different opportunities. And of course, there are some long-time references like Fuller, Rosenbaum, Rubin, Valiant, and Dever, which you can read in detail. Certainly, we can also do individual weighting. So non-probability sampling treated as a stage of random sampling with unknown probabilities. The assumption is that the participation is a random phenomenon. So the pi I had here is treated like inclusion probabilities in a random sample in this way. And that's what we try to construct. The problem is often that you have a high variance of the estimators in this model, and you replace the pi i's by mean of similar observations. This helps a little bit to reduce the variability of the weights, I think, and that's what we observed from time to time, especially if you try to use several variables, the weights tend to vary quite a lot. And here, of course, it's kind of philosophy. How much do you want to restrict this kind of variability of the weights? If you try to cut it down too much, then it's problematic, but it's less vulnerable with respect to model misspecification, at least in the case where you use strong kind of model assumptions. Then, of course, you can group weighting and post-stratification. So the weighted class proportions are calibrated to those of our response set. We are replacing the inclusion probabilities by post-stratification weights of propensity classes. Certainly, we have to construct these kind of classes, and that's not always extremely straightforward. You have to be a little bit careful how to construct these kind of data. See a little bit that my slides are running out of the picture. Okay. So, and a big class, which I like very much, which you certainly can do after using these kind of propensities or well, grouped propensities, is a calibration model. So with a calibration model, you try to construct extra weights, so such that the estimates, if you use these kind of weights, meet known totals. So you need some totals to be known. Often we know like the number of men and women in the proportion, you know, the age classes and so forth. And you can try to use this kind of information. It not necessarily has to be one-dimensional margins. It can be also a little bit higher dimensions. What I will warn a little bit is if you take too much auxiliary information, then of course you may end up again in kind of high variability of weights. So the most well-known one is the Greg estimator. This is kind of one representative of the general calibration model. Raking is another one, and I think here's the very nice article from De Vil and Sandal in '92. But earlier work, of course, was done by Deming and Stefan in '94. 40. So the known population totals as calibration targets, and exact compliance often reasonable, but once you want to claim exactly, then of course you probably have a high variance on weights. If you have only some information, like only gender and age classes, both one-dimensional, then of course it's unlikely that you have, unless you have very small classes, that you run in this trouble. If you have more auxiliary variables, you can easily run in that. And often, of course, this margin information is not known on universe level. And then, of course, you have to estimate that. So estimated calibration targets might be an issue. And then, of course, you have observer error inside. And why should you calibrate against estimates in an exact way? Probably you want to relax that. And there are different kinds of approaches, like from Chang-Kot, De Ville, Sandal, De Ville, and others, and so forth. And you can relax that by this kind of epsilon. So you're in an environment around 1. The additional constraint might be try to minimize the deviance from the epsilon to 1. So that's exact compliance, and you want to make sure that our epsilon is not so far away from 1. But you can certainly include that. And Gugemose and Tillet introduced penalized calibration in the GREC, and that's one of the things where you have kind of upper and lower limits. So each epsilon is either fixed to 1 or unconstrained in some way. What you also could do is thinking about the variation and try to minimize that. Well, I'm sure that all of you know Andrew Gellman's famous article, "Server weighting is a mess." And the big issue, well, that's in the Bayesian context. Even if I'm not a Bayesian, of course, this has to be considered here. But he talks about classical sample service, and even there, the variation of the weights can cause a lot of trouble. So certainly with non-probability samples, you also have to control that. And what we did is somehow we said we have the upper and lower limits. And I think Zhao Limeng in the joint statistical meeting, I forgot a little bit the year, in 2009, he phrased that, well, it should not exceed 10, this maximum over minimum weight. And well, for all of you who are working with design weights know that's hardly met. And beyond 100, it's dangerous. That's one part of the story, but surely we have to be somehow careful. So we somehow introduced 2 different kinds of box constraints on the one thing, and try to reduce the Gell-Mann factor. On the other way, we use kind of duality approach to see when can we somehow conclude about this kind of soft calibration as we use that. And there are, of course, other things like functional form approach, Estevao and Sandal, or Folsom Singh, and others have done a lot. So it's more like you have instrument variables and kind of model and try to calibrate them. So you see there are a lot of variants with the calibration approach. And and also with the response model. I don't want to go too much in all of the details because there's really much to say only on weighting, and you can certainly put that also in the raking context and logit modeling and so forth. And it's very interesting to go in some of the details. And also here, like Chang and Koch propose kind of relaxed constraints. And you see again, it's somehow similar that you have this kind of epsilon. So the ideas are similar. The question is, how is it used? And here we see it directly, like in the penalty function, you try to reduce that. We went a slightly different approach. So simultaneously thinking about the design weights and this kind of additional deviation from used by the epsilons. Certainly, there's also kind of model-based approach. You could do linear regression. That's one of them. But certainly also kind of other types of things like support vector machines. My former PhD students, you will see the reference soon, has been working on support vector machines and using that and try to get better information on these kind of weighting processes. And that, of course, is very interesting stuff. Even so, sometimes it seems to be kind of a little of black box. I make it a little bit shorter. So generally you can say any kind of predictive method could be used. What we encountered a little bit that sometimes predictive methods, depending on the sample, how you were drawing it, is somehow not in line with the full data set. And so you might think about doing something on top, additional weighting. Well, in small area context, you call it benchmarking. In the microsimulation context, you call it alignment. And these methods might be considered. You can include that either in the likelihood as a constrained likelihood or as marginal information. There are a lot of different things, and that seems also very promising. And as I said, I would give you the reference, and Simon Lenau, you see 2023, we had the defense right before Christmas, and I guess in a few days that will be available on the University of Trier PhD server. It's 417 pages as PhD dissertation. You can see there are an awful lot of methods inside, and also many of these machine learning things, and also with comparisons. And I also want to refer to the research project Ingrid, and the deliverables are referenced here. Once you have the slides, you just can click on that. And there's, I think, the deliverable 11.8, where we were talking about non-probability samples. If you go one step further, the question, of course, is what happens? Oh, there's a question. I'm sorry that I didn't see that. Yes, the epsilon. The question was, is epsilon simply a relaxation factor of the calibration weights? Well, not really of the calibration weights itself, I would say. It's more or less in general with calibration, and once you use the weights, you get the estimates. You want to make sure in the range of these kind of estimates, and that you're as close as possible, well, that you are exactly meeting the estimate of the known total. With this epsilon, you say, well, probably you can be around that, like 10% to the upper or lower bound, or even more or less. And that gives you big advantages. And especially once you have the trouble that the constraints are not fully met, or your weights bump up a lot, that's a big problem. So I think we had some very good success in some similar contexts, not non-probability, but in the German census 2011, we had the problem that in some communities, there was a bigger deviance using just the GREC, and also in terms of age and gender proportions. And just using this kind of relaxed constraints helped a lot to get better weights and not to have this kind of strange estimates in extreme cases. It can simply happen with some few elements of the sampling that extreme cases happen and the weights bump up. And with these soft constraints, you're in much better shape. But of course, it takes a little bit a while to understand how they work. In our approach, you see it with the Lagrangian, whether the kind of what constraints might be problematic. And you could rethink, well, you could start with kind of small range of the epsilon, then you see is there still some difficulties, and you relax it a little bit further. It's not really extremely computer intensive. So sorry about the delay, but now coming back, what happens then in big data? Well, obviously, it's in principle similar. The only thing is that now you have a really huge data set. And so you can read that in Yang and Kim. And well, with the big data, you have that variable of interest. The rest could be designed as before. The only problem is, like with big data, the question is, what is the complexity if you want to perform these kind of procedures? Do all of the other methods, including modeling, work as well? Can tell you, like the machine learning algorithm, they're really problematic, or nonlinear prediction methods, you will see one a little bit later in the examples, might be extremely difficult to be performed on big data. And here I can say that already now, you may think about techniques to do subsampling in the big data by two reasons: to reduce the complexity, and the other reason is probably to get a better kind of representativity. Whatever it is, if you want, we can discuss that later on. So in this context, often, but also in the other contexts, well, we talk about kind of missing information. Well, if you go back, we could use the big data set to impute that. And that means well, probably we can take record linkage. That would be nice. At least in Germany, we have some legal constraints depending on the sources you take. Then statistical matching, but then you have very strong assumptions, multi-imputation, mass imputation. So there are these kind of, well, linkage, matching, and imputation methods. But here, of course, you have to think always about the model assumptions. In general, conditional independence as an assumption is very hard, or at least it can hardly be verified whether it's right or not, unless you get some additional information from other constraints. So that was kind of rough overview. And now I want to come a little bit to examples. And this is an example from our wage indicator survey, which we had in the INCRIT project. We took the German part of the data and we're somehow looking at the distribution of the income classes. And what you can see here, the red ones is from the wage indicator survey and the blue ones is the income distribution from the German microcensus. The German microcensus is, I think, our largest household survey in Germany. It's 1% sample, so roughly 820,000 inhabitants are in the sample. Not everybody, of course, is working, so you have to reduce it a little bit and you have to consider design. But what you see, of course, is here a really selection bias. Well, it's trivial, of course, well, because who is willing to participate in the wage indicator survey? In general, those people who have these kind of jobs where it's interesting to understand a little bit the differences in wages. And then you see that more high incomes are very interested in this kind of survey. And the question is, of course, what method can you use here? So we already see, well, here's kind of deviation, but especially here in the core area, you have a lot of deviations, and these, of course, have to be controlled. And you see here we have quite a few of classes, and the question is, how do the different methods work? Well, this indeed is a real example, and we were treating it in two ways, as you will see soon. But before that, I look at the deviances between the microcensus and the wage indicator survey. And here you see the absolute values. So, well, you have, of course, here kind of under coverage by the wage indicator survey. And here you have an over coverage. It seems to be not that difficult here. But if you look at the relative deviances, then, of course, the highest class is the big issue. You have almost nothing in the microcensus. Well, this also has to do a little bit with the kind of cutoff classes in the microcensus. But in the wage indicator survey, you have a lot. And this, of course, gives you some headache. And what I will not present here, but which you can read in our deliverable is, of course, what do we do with the extreme kind of classes? We were doing it more in kind of classes. We're working on that. And for that, as I said, we did two things, a simulation study, and then, of course, the real data one. So the simulation data set was used on our Amelia data set that was coming from an earlier project, but only a part of the universe with 20,000 inhabitants. We took 1,000 Poisson samples of size 1,000, which is 5%, and with different kinds of participation probabilities. So, and certainly we wanted to somehow fix correlations with gender, the ISCAT levels, the basic regions, and age. And of course, the varying correlation with income and the INC variables, so household personal income, and these were very important. The inclusion probabilities were assumed to be unknown. Well, of course, we have to do that in a kind of probabilistic context, even so we don't know these inclusion probabilities. And if you're interested in Amelia and more, that's, of course, in our source from Pablo, myself, and some other co-authors. So I hope you have a big monitor. Otherwise, it's a little bit difficult to read. From left to right, we have 3 cases with no correlation, 20% correlation, and 40% correlation to the income. And we have from left to right, unweighted GREC, relaxed GREC, propensity scores, GREC plus propensities, logic calibration, ranking calibration, linear regression, Heckman model, and the support vector machines. And what we see, of course, is, well, here, unfortunately, the relaxed GREC in no correlation, and the support vector machines were a little bit problematic. But once we get in correlation, then it seems that these methods work quite fine, whereas the others are somehow overcompensating a little bit these kind of effects. The red line is the true income which we have here in our context. So the second part here is now between income and household income. And then, of course, that is somehow different. Again, we are estimating here, well, now we're estimating the correlation. It seems that many of the methods seem the same, but here we see that we have severe difficulties like with support vector machines, the Hackman models, and linear regression. So the prediction models seem to have kind of problem. And I think that's an effect which sometimes is known in imputation. I think Florian Meinfeld has written some nice articles on that, that the correlation structure might be problematic if you're really interested in them. And for the others, it seems not to be too bad, but again here, so this relaxed graph, even if the difference is small, seems to perform slightly better than the rest, at least if there is some correlation in the data. Certainly, we did that also with the real survey, but the survey gives you only one estimate. And it seems here that the propensities, and that we encountered that often, are kind of in the extreme case. And I'm pretty sure that especially the very low and the highest income class give you problems in terms of compensation. The others, the unweighted, of course, is the most extreme case. But again, here, the relaxed graph is somehow compensating a little bit and not overcompensating these kind of extreme classes. And if you're like in the mean household income, it seems something similar, so that some methods are really overcompensating, the others are somehow relaxed. But amazingly, the support vector machine goes in the entire different way. What does it tell us? Well, it's very difficult to say in advance what we really should take. Personally, I would always stress a little bit, never go just for one method, try to learn probably what method would somehow tend to overcompensate or undercompensate the outcomes. And then we have a similar problem like multiple testing. So finally, two short examples in the use of big data. I think I soon have to come also to an end of the lecture. And one is from Twitter sentiment analysis, and the other one is from quality measures of satellite images. We did some research on that. And here again, I think Katharina knows quite a lot of using Twitter data and small area statistics, and especially on the use in auxiliary data, and that works quite well. It's always easier in reality if you don't have the trouble directly on the target variable, but more on the auxiliary variable. So what happened, and here I come back a little bit to the to elections. Now it's Biden against Trump. There was a sentiment analysis in terms of natural language processing. So it's more the question, are the tweets either positive or negative with respect to Biden or Trump? And I can tell you that, of course, is, well, our language department works a lot of that, and that's not easy and straightforward. Sometimes like ironic answers cannot be determined quite well, but at least it gives you some impression. The big advantage, as I mentioned that before, of course, is that you can somehow see it during the time. So as a permanent stream and see, do things change? My personal opinion here is that classical opinion research is a little bit in disadvantage in terms of elections. Why? Well, if I look at the last elections, that was both Trump elections, that was, of course, the Brexit, also elections in Germany, a lot of things happened quite at the end. And it seemed that the information, who is an advantage right prior to the election, gives a lot of impact to motivate people to go to the election finally. And that's why I'm in favor, like I think France disallows opinion polls within the last 2 weeks prior to elections. And that I think is good, because we don't want to influence directly on kind of direct information. Nevertheless, it happens. Like years ago, we had a big flooding right prior to the elections. And at that time, so the Chancellor Schröder was running around and the polls changed quite a bit. So here we are on the Twitter data. And well, these tables, some of you who have been working with that know them, of course. It's quite a lot of information with these kind of tweets. And if you look then at the positivity proportion per state, like by the Twitter data, you see it's varying. Sometimes there are bigger differences, sometimes smaller. It's like in the elections. But the question, of course, is what happened finally? And if you look in some details, so then especially we see like in Arkansas and Idaho, the Twitter data were completely in the wrong directions. And in line were more or less the big ones like here in Maine, California, and New York. So it can be somehow used, but it's extremely difficult. And the sensitivity towards what is positive and negative seems to be very high. And definitely it's not representative if you use Twitter data. I can tell you that just the regional information for Twitter data, of course, is extremely difficult to gather. If you go to satellite images, and I think that's one of the most well-known areas because a lot of data are in the meanwhile available by well, different types of satellites and the NASA and other institutions. It's very interesting to have this kind of spectral data and work with them. Of course, you can somehow measure several things on the ground, on plants, streets, and whatever, and that helps you quite a bit. And what we did a while ago is with our colleagues from remote sensing to look for the Rhineland-Palatinate forest inventory. So what we were interested is timberwood reserves and the biomass to estimate that. We used somehow the airborne laser scanning data from 2002 to 2013 to understand where do we have on the ground this kind of timberwood. And then, of course, there is a forest inventory. It's a kind of grid over the surface where they collect direct information. Now you see here, of course, we also use this kind of big data in terms of auxiliary information. And then we worked directly on that. Now, I don't want to step towards small area methods in much details, but just taking the sample information on the ground with a 2 kilometer by 2 kilometer grid is not precise enough if you want to estimate the timberwood. Using this additional information, of course, makes it necessary that you have adequate methods. And since we have several districts where we're interested in timberwood reserves, of course, we use small area methods. The problem is, of course, that the classical Batiste-Harder-Fuller model uses a linear relationship. And if you look at the canopy heights and the timberwood volume, then, of course, it's a highly nonlinear process. And the first attempts, like if you would try to go for a linear regression, you can see what happens here. We had in some areas negative estimates. We don't know, there is no negative estimate. It must be positive by definition. And that's why we introduced somehow this kind of constraint, nonlinear regression model using B-splines, and that worked quite well. Well, if you're really interested in the results and how we did that, I recommend to read our paper in the Royal Statistical Society. And there we give also some results. The problem is, of course, it's a tiny bit of computer intensive. And that means that in the meanwhile, we also were adding some additional routines, which makes it possible to estimate that in higher dimensions. Here we use just the canopy heights, which is much easier. And with multi-dimensional splines, it's much more sophisticated. So to conclude somehow, data quality in non-probability samples and big data is really a big thing. It seems somehow that the classical concepts of data quality and total survey error hardly meet the needs for big data. We see some of the concept work and others are completely out of bounds. So that's why people work on that. I think very nice work is from Natalie Shlomo, Barry Schouten, and others on the non-response measures, the so-called R indicators, but there's also other things that at least give some impression. And but there's also other things like fitness for use. Can we use the data? I always say, be careful with all the approaches. You must understand your data, and you should be aware that you understand, are there any possibilities for selection problems? If yes, I always say, be careful. There's surely approaches in development. The paper of Beamer is very nice. And the big thing, of course, is that the inference, that is still an issue. So like variance estimation, accuracy measurement, that is hardly something which can be tackled unless you have strong model assumptions. So with Charlotte articles, I wrote an article, unfortunately it's in German, to somehow conclude some of the ideas and references are therein. If you look at what we did here, so we had the response models, calibration models, and prediction models. It seemed that this kind of combination of response and calibration together with soft constraints seemed to work best because it's not overcompensating. You can more easily control the weights. With the prediction models, you have to understand very much in detail what your models tell you. And probably, and I think that's not really well done yet, it might be worth thinking more about additional calibration or benchmarking for these prediction models. Certainly, we need good predictors and the right variables. If we have them, it gets better, but it's not really easy. But be careful, especially in big data. It may happen that some data are coming in several times. And then it's extremely important to think about editing, data cleaning. We saw on the wage indicator survey many answers which could not happen to be in practice. And that's where you have to be really careful on, don't rely directly on the data, be careful on what you have. So as I said, there's no general strategy, but it's case specific. In some cases, the things work really well. Weighting helps in special cases. Model-based methods might be better, but how to know? That's still something where I'm a little bit critical. I think Simon was very much in favor of the machine learning algorithms. Well, if you bump up everything inside and also with soft constraints, then of course you cover many of these methods. And the question is, well, how do you get the knowledge to work to bring them in the right way? So the non-probability samples, on the other hand, have big advantages, especially in terms of time. You can really get information step by step, especially like in these time-critical things. So especially if you have some kind of influential information which changes the results rapidly. And if you turn to big data, of course, traffic control, road use, these are examples where I say it's extremely difficult to set up very good surveys. So big mobile data might be really very important. Nevertheless, it's important to understand them. And currently, I think in most countries, they are extremely expensive to gather. And at least in the German market, I can say you have the three big players. If you have only one, it's extremely difficult because you have selection biases between the three big mobile data companies. Satellite data is wonderful and you have access to it. And that's in contrast to most of the other big data. I sometimes say that big data is nice, but it's a little bit against the old philosophy of open data. It's a closed area, it's difficult to access them. But in terms of satellite data, it's the opposite. And here we have nice examples. Urban patterns is something where we are working on. Sustainable development indicators are somehow very interesting areas to be considered, but there's a big but. Whenever we aim getting important information, like for budget transfers, please use proper high quality survey data where you really have the control on the quality. So in this case, neither the web data nor the opinion polls might be valid. Big non-response also is problematic. So thank you very much for your attention, and I'm waiting for your questions.
Yes, thank you, Ralf. Thank you very much for this very interesting presentation. Yeah. While we wait, if we receive any question for the audience, I don't remember because, as you said, we were both involved in the INVIT project on the wage. On the wage data, did you also compare them the distribution with EU Silk data? Did you have that opportunity? Not in German, maybe.
Well, we were certainly focusing on the German data, and the German Silk is still problematic. Mm-hmm. And well, what I also say, the Silk data by countries is not really large. So you're comparing the wage indicator against a small survey. So it's always a little bit of difficulty. What are you comparing with each other? In the German case, I think from last year on, the SIG data are much better because earlier there were some problems by the routine, how the German SIG data were gathered. And it's much better because it's now integrated within the microsensors, and that stabilizes a little bit the results. But well, once it is somehow included in the microsensors, I wouldn't use the SIG data. I can directly use the microsensors data because the SIG is a subsample then of the microsensors, and I would go for the big one.
Yeah, okay, sure. And I have also another question. I mean, because of course you don't want me to ask to advise, of course, but for the students, I mean, based on your experience on the compensation method, so thank you, of course, for your review, because we have students, I think more, maybe also you, but especially in PISA, for example, they're not so experienced in advanced statistical methods. So do you have for them any special suggestion, I mean, on where to start? So the methods that you think in general, I mean, I know you say that it's case specific, but in general, where to start? I mean, if they have to study some methodology, to start from something, do you have any suggestions or some method that you think are the more, I mean, the ones that you expect should maybe works better in general cases, if any, of course?
Well, that's really a good question. I don't want to be blamed for my own words now.
No, sure.
Well, even if I was somehow blaming propensity scores, that's at least the starting point. You have that in many packages and you can easily bump it in. But certainly I would also go for some other methods. We had some very good examples like with calibration and propensities, combining that. But here you had the difficulties. If you take too many auxiliary variables, you always run into difficulties with highly varying weights. So I would always look at the weight distributions and look, are there any really strange patterns where you find the extreme weights? And that's why I think this kind of soft calibration, either our routine, there were also some others, I think it's not that problematic which you would use, but like using this kind of allowing a little bit variability and not bumping it directly on these kind of hard constraints is worth doing it. On the other hand, with the prediction methods, something which I don't want to say loud, of course, so I say it in a secret way. I'm certainly in preference of this highly sophisticated statistical methods, but sometimes the machine learning methods are, with the packages, easier to apply. The only problem is you don't know what really happens. And the inference is a bit of a complete nightmare then, but you can compare that. And personally, I would use 3 strategies and then see a little bit what happens, and try to understand a little bit other differences, like if all methods with some auxiliary variables come to the same result, you're on the safe side more or less, unless you have extreme examples. It would be interesting to see an example where all these methods give you the same results, but the truth is somewhere completely different. Yeah. Well, as I said at the beginning, like what Jelke or Bert Hulliger told me about this kind of religious subgroups in communities. You don't observe that. And then, of course, it seems that all methods go for the same direction, but the real result is something different somewhere else. But that was a big motivation for a small subgroup influencing that heavily, these 2 surveys. And I don't know the details anymore, but that was extreme. Unless, and that's why I would always think also about the content. How is the data gathered? And could there be kind of motivation for a small subgroup to influence that? And if yes, I would look for auxiliary variables, which might be able to at least cover something. Yeah, but well.
I agree. I agree with your suggestion, yes.
So not unobvious to go this direction, but that's what I would do. Certainly, as I said, whenever it's really important and you have balance of budgets or whatever, I would always go for this kind of real, well, official statistics surveys, and with that, which are most likely mandatory. And I don't want to see politicians going for this kind of web service and having important decisions in the parliament just on this kind of web data. That would make me very nervous, to be honest.
Yeah, and that's why we are here, I think, also with EMOS.
Yes, sure.
Yes, okay. So Ralf, thank you. I don't see any other question on the chat. So I think we're also, it's 3 o'clock, so I think we can close here. So thank you again for this very interesting presentation. And of course, I thank all our participants who joined us today. So as participants, you are invited to fill in a short survey about today's webinar. The survey will open in your browser after the end of the Zoom meeting. If you don't have time right now, you will receive a link by email to fill in the survey later. We'd really appreciate your feedback to further improve the EMOS webinars. So our next webinar is scheduled on February the 8th of February, when Professor Walter Radermacher will be presenting on statistics for the public good. So for these and for future webinars, please keep an eye out for our website, emos-events.com. So thank you again, Ralf, for this webinar, and thank you for now to all of you. Have a nice day.
Thanks a lot. Take care. Bye-bye.